Our ninth presenter is Junwon Seo, whose presentation is titled Additive Manufacturing of Metallic Components. We Bake Rocket Engines.
How many of you have baked a bread? How many of you have tried carving a bread into that shape? I haven't either, because that would create so much mess and so much waste that my roommates would be pretty upset. Unfortunately, this is how things are still done in the metallic industry. Whenever we want to fabricate complex geometries like rocket engines, what we do is we would get this huge metallic plate and use those drills to carve out the shape and weld them together. Not only is this process complicated, but it's also very bad for the environment because it creates so much material waste. Now, my research tries to answer this question. Can there be a more clean and economical way of fabricating these complex geometries? The answer is within that fluffy teddy bear bread. That teddy bear bread was made by stacking and merging these flour dough together to form a shape. And this was put into an oven to be baked to become a single solid part. And we do the same for metals. We get these metallic powder. We stack them on top of each other, and we use laser to fuse them together to form a certain shape. And then once we form the shape that we want, we would put this into a furnace to strengthen it. Now, this is a novel process, so we need to do process optimization, basically figuring out what laser power to use and at which speed the laser should be moving at. And we, again, do what the bakers do. Do you know what bakers do when they invent a new bread? They cut it in half, and they look at the cross-section. And when they look at the cross-section, they're able to tell what it's going to taste like, what the texture is going to be like, and most importantly, how the baking process can be modified so that this bread can be more delicious. And we metallurgists have the same ability. Once we print these parts, we would cut them in half and look at their cross-sections. And by looking at their cross-sections under the microscope, we're able to tell how strong this will be, how long it would last in a certain environment, and most importantly, how we should modify the process so that this atomic structure in this micrograph can be optimized to have the most strength and the most durability. And using this process and research technique, our group was able to fabricate complex geometries with this alloy called Haynes 282 that has the same strengths as the ones that have been conventionally manufactured and actually has better durability than the conventionally manufactured Haynes 282, but without creating material waste. With this research, this can be applied to a whole variety of applications such as rocket engines, heat exchangers, and even turbine blades. Ultimately, I see my research revolutionizing the manufacturing industry by making it more clean, sustainable, and built for the future. Thank you.